In this video, we are going to learn in detail about how to calculate the 18 electron rule for either the bridged or the normal complex using neutral method and oxidation method. In my previous video, I have discussed about the ligand contribution for both of these methods. If you feel like you are memorizing these values for neutral and ligand contribution for both of these methods, you can watch that video because you don't really have to memorize those values. It is very easy if once you understand. Okay, let's move on to here. So first example, so heptacity is 5, C5H5. C5H5 is nothing but cyclopentadiene, and then iron is present, and then CO2 is present, and then chlorine is present. Now we are going to calculate the 18 electron rule. So first we will neutral method. This side I'll take neutral method and this side I'll take oxidation method. Okay. So in the case of neutral method, you don't have to calculate anything like you don't have to know the oxidation state of this particular ion. Just you have to know the electronic configuration. Ion is 4s2 3d6, right? So totally how many electrons are there? 8 electrons are there. I'm just writing that 8. Then plus. Then for neutral atom, whenever your ligand contribution, if you are noting, if they have given this heptacity, here the 5 is the heptacity, you can just take it as 5 for neutral method. You don't have to do any calculation or anything. Then for carbonyl group, it is 2. So how many times? 2 2s are 4. Then for chlorine, it is 1 because chlorine will have only one electron that will bond in the case of neutral. So it is 1. Okay. So if you calculate this, it will be 16 electrons totally. So then in the case of oxidation method, first you have to calculate the oxidation state of the metal. For metal, I am just taking as X. Okay. And then for carbonyl group, for this group, what will be the charge? Formal charge is 0. Then for chlorine, what is the formal charge? -1. For chlorine, it is -1. Then for this cyclopentadienyl compound, what is the formal charge? It is also -1. So equal to 0. So X will be what? +2. So Fe is 8 electron, then Fe2 plus will be how many electrons? 6 electrons. Okay. So now for Fe, I will just take it as 6 electron. This is for Fe. Then for carbonyl, the contribution in oxidation state is also 2. Okay. Then for chlorine, the contribution here is 2. So I am writing 2. Then for cyclopentadienyl, so if you can't understand means just note this. Okay, if it is a metal and then chlorine is bound here, 1 2 3 4 5 6 7 electrons are there in chlorine. You have to heterolytically cleave this. Okay, so what will happen? Chlorine 1 2 3 4 5 6 7 8, so -1 charge. That's why we are putting -1 charge for chlorine, and then 2 electrons are basically involved here. That's why for chlorine I have written -2. Then for cyclopentadienyl, it will look like this. Okay, here also metal will be there, then this electron will go here, so it will be like this. Okay, metal, and then this will be like this. Okay, so 2 2 3 4. Okay, so totally how many electrons? 6 electrons. So if you add all these electrons, it will be how many? 16 electrons. So both will get the same answer. If it is not getting the same answer, then it is wrong. You have done it wrong. Okay, so let's move on to next example. CH3, Mn and CO5. Okay, so here metal is there. Metal is manganese. So first we will write the here neutral. O means oxidation method, N means neutral method. So manganese oxidation state is 4s2. So instead of just for this particular electronic configuration, just know the order. Okay, scandium, titanium, vanadium, chromium, manganese, copper, and then zinc. So this one we know. For first one you have to know 4s2 3d1. So how many electrons are there? Totally 3. So 3 4 5 6 7 8 9 10 11 12. So basically whatever it is coming down also, it will have the same number of electrons. Just know the 3 4, just the order you have to know for everything. Whatever, even if it is 4d or 5d, you have to use the same electron. Okay, so for manganese it is 4s2 3d5. Okay, so now first let's calculate the oxidation state. Let's come from oxidation state method. So for manganese I am taking as X. For this CH3, the charge will be, formal charge is -1. Why? Because the metal is connected to this CH3 bond. So one electron is the CH3. Now heterolytically, if it is cleaving means it will have two electrons now. So charge will be -1. Okay. Then for carbonyl it is 0. So X will be what? +1. Okay. So manganese, if it is losing one electron, it will be 4s1, 3d5. So totally how many electrons? 6 electrons are there in manganese. Okay. So for manganese I am putting 6. Then for carbonyl you will add 2, right? So 5 2s are 10. And then for CH3, what is the contribution in the case of oxidation state? It is 2, because as you can see these 2 electrons will be donated, so the contribution here is 2. Okay, so the answer will be 18 electrons. Coming to the neutral method, in the case of neutral method, the same manganese, what will be the total number of electron? 7, because 4s2, 3d, 5. So 7 electron. Then for carbonyl it is 2, so 5 2s are 10. So already I have discussed about why carbonyl is 2, right? Carbonyl group will look like this. So it will have positive charge and then this will have negative charge. So overall it is neutral, plus and minus will cancel. So these 2 electrons are donated. So whether it's oxidation method or neutral method, the number of electron is going to be 2 only. Okay. Then for CH3, how many electrons is donating? 3 hydrogen will have 3 carbon electrons, and then only 1 electron is remaining in carbon, that is only is used for neutral method. So it is 1. Okay. So now if you calculate the total number of electrons, it is 18 electrons. Okay. So let's move on to the next one. So molybdenum, it is present. So cycloallyl group. So this is an allyl group. And then this is bent nitrosyl. Okay, bent nitrosyl and linear nitrosyl, they both are different. So this one is a bent one. Okay. So if you see here, so let's move on to, first we will see the neutral one and then we will see the oxidation one. Okay. So for neutral, what you have to do is, we have to know the electronic configuration for molybdenum, right? So molybdenum, basically 6 electrons will be there. So chromium, downside of chromium only you will get molybdenum. So it will be 6 electrons. Okay. So molybdenum is equal to 6 electrons you are having. Then for this particular allyl group, so this is the allyl group. Okay, CH2 and then CH and then CH2. So this CH2 will be bound to our metal. Okay. So here for neutral, what will be the contribution? See, they have given, whenever they have given like a dotted, these 3 carbons also it is involved. Okay, 3 carbons. Basically the heptacity is 3. So once the heptacity is 3, we know that the neutral, what it means, the neutral ligand, the contribution will be 3. Still I'll tell you how. Okay, for these two electrons here, okay, that is 2 electron, and then here if you homolytically cleave it, for whenever you are doing for neutral method, homolytically cleave the metal ligand bond. Okay, so here 1 electron and 1 electron. So CH2 will have 1 electron remaining in it, right? Already it has 3 bonds. So of course 1 electron is remaining. So 1 electron. So 1 plus 2, it will be 3 electrons. So for neutral method, it is 3 electrons. So here also the heptacity is 3. Here the heptacity will be what? Whenever they have given a round like this and they have linked like this, it means that all the carbons are involved. So heptacity is 5. So the contribution will also be what? 5. Why means? See, if you take it like this, cyclopentadiene, it will have 1 electron here. Because metal will have 1 electron, we have homolytically cleaved it. This is the bond that was there. Okay. So this 1 electron is contributing. So it is 1 electron. So 1 electron, here 2 electron, here 2 electrons. So totally it will be 5. Okay. So now if you calculate means, so then we will move to nitrosyl. So for this one it is 5, for this one it is 3. For nitrosyl, how you will know? So it is basically bent, right? And then 2 lone pair is there. So if you homolytically cleave it, here 1 electron, here 1 electron will be there. Okay. So molybdenum will have 1 electron and this will have. So basically this electron is bounding. So basically the contribution here is what? Only 1 electron. So now we can calculate, right? So what is the total number of for molybdenum? I am writing 6. and then this one 1 3 and this one 1 3, so 3 plus 3, and then for this one I am writing 5, and then for bent nitrosyl, what is the value I have to write? That is 1. So totally you will get how many electrons? 18 electrons. Okay. So this is in the case of neutral method. So moving on to the oxidation method. So in the case of oxidation method, you cannot use the heptacity thing. This heptacity thing is not valid in the case of oxidation method. First you have to find the charge. So to find the charge, what you can do for molybdenum, it is X. I'm taking it as X. And then for this particular group, I mean the allyl group, what will be the charge means? So basically, so this is bound to the metal, right? So what will happen? This two electrons. So whenever finding the charge, you have to heterolytically cleave it. So two electrons will come here. So it will look like this. Okay, CH2, and then two electron it has gained. So if you count and see here, the carbon. So whenever you are putting charge, just count and see. It will be easy. So one electron, carbon, one electron is here, and then two electrons are given to this hydrogen bond. So totally three electrons are over, and then another one electron is here. And extra one electron is here. Like totally this carbon has 5 electrons. So the charge is what? -1. So for this heptacity 3, what will be the charge? For this one it is -1, and this one is also it is -1. What about here? So the molybdenum is attached to nitrogen, and then lone pair is there. So I have to heterolytically cleave, right? So what will happen if I heterolytically cleave? The two electrons will also, this is the new electrons that I got after cleavage. So this is the new electrons that I got. So now if you count and see, 1, 2, 3, 4, 5, 6, 6 electrons are there. So what is the charge will be here? It will be minus, right? Because it is having extra electrons. So it is -1. So for in this case, the charge for here is -1. Then cyclopentadienyl, if you see, means, so this is the ring. Okay, this is the ring, and then this is the metal. So this bond will have two electrons. So this will come to here. Then what will happen? So if we take it like this, so two electrons are there here now. So this carbon, this particular carbon here, if you see how many electrons it has one electron in this bond, one electron in this bond, 1, 2, 3, 4. So basically it has and then one hydrogen will also be here, right? One hydrogen will also be here. So that will have one electron. So totally how many electrons? 5 electrons are there. So it is having minus charge. Extra electron is there. So minus charge. So the charge is what here? -1. For this one is also it is -1. So now we can calculate the X. How many -1 is there? 4 times -1. Okay, so -4 equal to 0. So X will be what? +4. Okay. So once you know this, so molybdenum in +4 oxidation state. So actually molybdenum has 6 electron. If it is losing 4 electron, remaining there will be 2. Okay. Then what about the contribution? So in the case of contribution, consider this particular allyl group. Allyl group will basically contribute around this 2 electrons. Okay, these 2 electrons will be contributed to the metal. So allyl I am writing 2. 2 allyl is present. So 2, 2 I am writing. Okay. Then for nitrosyl, how many it will donate? This will be donated to, in the case of nitrosyl, right? So for that also I am adding 1, 2. And then for cyclopentadienyl, how many? 2, 3, 4, 5, 6. Right, 6 is donated. So 6, it will be 6. Okay. So what will be the answer? 6, 7, 8, 9, 10, 11, 12, 13, 14. Wait a second. Oh, sorry. I forgot this electron. Okay, here 2 electron, here 2 electron is there. So in the case of allyl, if you see, this one will give 2 electron, and this particular bond here, that is this CH2, and then this 2 electron will give 2 electrons. So totally 4 for allyl. Okay, 4. Allyl will have 4, 4 each. So totally how many electron? 18 electrons. Okay, that's all. So next example is molybdenum, then allyl, all three carbons are involved, and then nitrosyl in linear form, and then nitrosyl in bent form, and then cyclopentadienyl group is present, and then all carbons are. So whenever all carbons are involved only, we will get this the ring like structure. Okay, so the heptacity will be 5 here. What about the heptacity here? It is 3. Then so for neutral method, easily we can calculate, right? Neutral method for molybdenum, totally 6 electrons will be there. Okay, and then for heptacity, for this one it is 3, for this one it is 5. Then what about this linear group and this bent group? Okay, so in the case of linear nitrosyl, what you have to take is like this. Okay, for neutral method you can take it like this. Okay, why I am taking, so this is the metal, so M is the metal and nitrogen is here and then oxygen is here. So we can also take it like this. So both are actually same only. So here also N is in sp hybridization, here also N is in sp hybridization. That is why it is linear. Either one triple bond can be there or two double bonds can be there for sp hybridization. Okay. So what is happening here is, see, so here oxygen is having 2 electrons, 1, 2, 3, 4, 5, 6. There is no charge or anything because its electron is with itself. Okay. Then for nitrogen, 1, 2, 3. 3 electrons are bonded like a sigma bond. And then one lone pair should be there. That lone pair is acting as a coordinate bond to the metal. Okay. So the neutral, in the case of neutral, so the number of electrons that is involved, if you see, 1 plus 2. So this is forming that coordinate bond, and another one it is forming a sigma bond type. Okay, so in the case of neutral, it is how many electron? It is totally 3 electron. But if you want to consider in the case of oxidation method, what will be the contribution for this linear structure? Means you have to use this structure. It is better. Okay, so what will happen? So from this structure, you can derive this structure. Okay, how? See, metal is there, nitrogen is there, oxygen. So basically this nitrogen will have a positive charge because now this nitrogen is having only 4 electrons if you count and see the nearby electrons, and this metal will have negative charge. So this 2 electrons will come here and this 2 electrons will go there. So then what will happen? So metal, so this metal atom is gaining another 1 electron, so 2 minus, and then only one single bond is there now, and then nitrogen is there, and then here triple bond is there, and then oxygen is there and one lone pair. So if you count the electrons, 1, 2, 3, 4, 5. For oxygen only 5 electrons is there. So it is in lack of 1 electron, so it is positive charge. And then if you count for nitrogen, 1, 2, 3, 4, it is also in lack of 1 electron, so plus 1. So minus 2 and plus 2 will cancel out and it will be neutral. So to calculate this number of electron, you have to heterolytically bond it. So it will look like this. Okay. So positive charge, and then here see why I have written 2 electrons here, because this bond had 2 electrons. That 2 electrons I have taken it to the nitrogen. Now if you count and see 1, 2, 3, 4, 5. So you don't have to put any charge or anything because nitrogen has its electron as it. So here the formal charge will be plus 1 in the case of linear, but in the case of NO, if it is bent, means in the case of bent the charge will be minus 1. I have already told you in the previous example. For bent the charge will be minus 1. Here it is linear and the contribution here will be 2. Okay, the contribution here will be 2 in the case of oxidation state method. Okay. So in the case of oxidation state method, the contribution is 2 for this one, and in the case of like neutral method, the contribution is 3. Okay, so now we can do. For bent already I have explained for bent what will be the neutral contribution. In the case of bent nitrosyl, the neutral contribution will be 1. Okay, here what will be the contribution means for bent structure, bent means the contribution will be 2. Okay, so now you know the rest of the thing we can calculate. First for molybdenum it is 6, And then for nitrosyl linear, what is the answer? Nitrosyl linear means it is 3. And then nitrosyl bent means it is 1. And then cyclopentadiene 5 I can add. And then for this allyl I'll just add 3. So what will be the number of electrons? It will be 18 electrons. Similarly for oxidation method, for first we have to calculate the oxidation state. For molybdenum I am taking it as X, okay. I have took it as X. And then we have to know the charge for each of these. For linear, just now I told it is +1, right? Formal charge will be +1, okay? For bent, it will be -1 charge, okay? And then here also it will be -1 charge. Here also it is -1 charge. So totally how many? So -3 and then +1 equal to 0. So X will be what? +2. So molybdenum in +2 oxidation state, how many electrons will have? Initially 6 electrons was there, now 4 electrons will be there, okay. Then coming to the contribution. So how much each will contribute? This allyl group will contribute 4 electrons, okay. So because this will donate 2 electrons and this sigma here 2 electrons will be there. So totally 4 electrons will be contributed by allyl. And in this particular cyclopentadiene group will contribute 6. Already in a previous one we have seen. Then for linear group, what it will contribute? Just now we saw for oxidation linear it will contribute 2. And then for bent also it will contribute how many only? 2 only, okay. So if you calculate it, you will get the answer, that is 18 electrons. So I hope you understood this problem. Then this is a very important example, titanium. It is bound to a metal, a carbon group compound. And then here it is like this, okay. So here if you see, whenever this round is present, the heptacity will be the total number of carbons. So total number of carbon is 5. Here total number of carbon is 5. Here if you see, this titanium is bound to only one carbon. So heptacity is 1. Here also heptacity is 1. Okay. So for neutral method, here easy, very easy to calculate. Okay. Then for first we will see the oxidation method because that is the tough one. Okay. For oxidation method, each will hold a charge of -1. If you see here, this is the metal bond and then this electron will come here. So it will look like this. Okay, 2 electrons will be there. So -1 charge because the carbon in this particular carbon will have 5 electrons. If you exactly count and see, don't forget that here one hydrogen will be present. Okay, so you have to count and see. I can count and tell you for once. Okay, so this is the carbon. Now this carbon got 2 more electrons. Basically this carbon is now having 5 electrons. That is why we are giving -1 charge, because here one bond is here. In that one bond, 1 electron will be from carbon. And here one bond is there. There also 1 electron will be from carbon. Here also 1 electron will be from carbon. 3, 4, 5. That's why we are putting what? Minus sign. Okay. So here all of these things, this one, everything will have a -1 charge only. Okay, everything will do the same -1 charge. So the metal titanium is 4s2, 3d2 electrons. So totally 4 electrons. Okay. So now if you calculate the oxidation state for titanium, I'm putting my X, then -4, right? Because 4 times -1. So X is equal to +4. So the titanium in +4 oxidation state is equal to 0 because 4 electrons are lost, it will be 0. Then to calculate the oxidation method, first value is 0 for titanium, and then for this one, what will be the value? If you see means, you should be very clear here. It is not 6. See, this is the difference. Okay, one group is like this and another group is like this. All the atoms are bound. So this is the difference between the round group. This one is similar to the round one. Okay. So basically how to calculate here, if you're going to calculate, the heptacity is 1. Only this carbon we have to consider. Okay. We should not consider other carbons. So whenever there is a heterolytic cleavage, there will be electrons, and this 2 electron only we have to consider. We cannot consider all the other things in this case. Okay, so the value for this one will be 2, because 2 times this group is present, 2 plus 2. Okay, then another this one, in this case here 1 2, here 1 2, and then here 1 2, so totally 6 electrons. So since this is present 2 times, this one 6 electron, this one 6 electron, 6 plus 6. Okay, so totally 16 electrons will be present. Okay, in the case of neutral method, it is very easy to calculate. So titanium total number of electron is 4, and then for this one heptacity is 5. 2 times I am writing 5, 2 compounds, and then this one heptacity is 1. So 2 times 1, and then totally 16 electrons will be there. Okay. So now is the important part. Okay, bridged ligands. We are going to see for bridged compounds how everything is. We have to calculate everything. Okay. So this compound Fe3CO12. So mostly whenever there is more than one metal, there will be metal-metal bond and bridged compounds. There are cases where there won't be any bridged ligands or anything. There may not be metal-metal bonds. It is not compulsory. Okay, so you just have to know that. Okay, so whenever you are mentioning a bridged ligand, we will mention like this. Mu will be used to mention the bridged ligand. Okay, so now they have given this compound and asked you to find what is the number of metal-metal bonds in this compound. How you have to find it. Okay, so first what we have to do is we have to calculate the total number of, whenever there is bridge, just use the neutral method. Just don't prefer oxidation method at all. It's very tough, so it's better to use the neutral method only. Okay, so 4s2 3d6, it will be the total number of electrons, so it is 8 electrons. So since 3 times 8 is present, so 8 into 3. Okay, and then for carbonyl it is 2, right? So 12 into 2. So what is the total number of electron here means 48 electrons are present. So now actually what is the procedure? What we need for a stable compound, each metal should have how many electrons? 18 electrons. So here how many metals are present? 3 metals are present. So 3 into 18 electrons should be present, then only the complex is stable. Okay, so 18 into 3 should be present. But what we have only 45. So we are minusing it and checking how many electrons we need for stability. Okay, so what will be happening? 54 minus 48 is equal to 6. So our particular complex is in short of 6 electrons for stability. That is what we have understood here. Okay. So now what is this 6 electrons? How to attain the 6 electron means now you are going to use metal-metal bonds to attain the 6 electron. So one metal-metal bond is equal to how many electrons? 2 electrons. One metal-metal bond is 2 electrons. So here how many electrons are there? 6 electrons are there. So just take it as X. How many metal-metal bond will be there? So cross multiply this. So X into 2 is equal to 6. So X is equal to 6 divided by 2. It is equal to 3. So 3 metal-metal bonds will be there in this particular compound. Okay, because if you see 3 metal-metal bond. So all these 3, here 1 2 electron, here 1 2 electron, here 1 2 electron, totally 6 electrons. So this particular complex will be now stable. So now we have to check. So consider Fe. I am writing like this: Fe, Fe, Fe. So they have given the 3 metal-metal bonds. Maybe I can put it like this. Just like that, we can remember. We can put it like this. This is one of the possible way to put the metal-metal bonds. But if you see these one Fe. Like one Fe is bound to 2 Fe. Okay, that is one Fe has 2 metal-metal bonds, right? So how to know that? Like one Fe is having 2 metal-metal bond. How to know that particular thing means? First, what you have to do? Take the total number of electrons. Okay, take the total number of electrons and then divide it by 3. Because this is the total number of electrons, I am going to share these electrons with the 3 metals. Okay, just sharing. Okay, so it will be 16. So now each metal is getting only 16 electrons. Okay, So now each metal needs how many electrons? 2 electrons, right? Each metal needs how many electrons? 2 electrons. Okay. So if there is one metal-metal bond means, see, if there is one metal-metal bond, so consider this Fe. This Fe now needs how many electrons? So already carbonyl is all present. Now this Fe is having 16 electrons. It needs 2 more electrons. So that will be given by the metal-metal bond. So if from this metal-metal bond 1 electron, and from this metal-metal bond 1 electron will be taken. So one metal-metal bond can provide only 1 electron to a Fe. Both the metal-metal bond, because one metal-metal bond can have 2 electrons, but the 2 electrons cannot go to this Fe itself. Okay, one metal-metal bond can give only 1 electron to a metal. Okay, so if this electron is going to this Fe and this electron is going to this Fe, and then again another 1 electron will be present, that will go to here. Here 1 electron is present, that will go here. So if you see, each metal is gaining 2 electrons. So from this idea itself, you can understand that if it is in short of 2 electrons, so that 2 electrons will be given by 2 metal-metal bonds. So basically from that itself, we can understand each metal will be bound to 2 other metals. Okay, then other rest of the thing, the 12. So 12 carbonyl is present, 12 divided by 3. You have to share between 3 members, right? 3 4 so each Fe will have 4 carbonyl groups to balance it. So if you count and see, you can easily understand. So here 2, 2, 2, 2, and then Fe how many? 8, and then here 1 and here 1. If you this is for one metal. So if you calculate, it will be 18 electrons for each metal. Okay. So a little more complicated one, if we understand, it will be very easy. So CO4 and then CO12. If you see here, this is cobalt. Cobalt means 4s2 3d7. Okay. So totally 9 electrons are there. So first we have to calculate the total number of electrons. Okay. So 9 into 4, and then carbonyl is 12 into 2. So the total number of electrons here is 60. So actually each should have 18 electrons. So 18 into 4, that should be the total number of electrons. We are going to check how much it is short. So if we check the shortage, it will be like around 12 electrons. So basically this is in short of 12 electrons. So we need how many metal-metal bonds? That we are one metal-metal bond has 2 electrons. So how many metal-metal bond will have 12 electrons? So just cross multiply. So X into 2 is equal to 12. So X is equal to 12 divided by 2. So 6 metal-metal bonds are there. So now I have found that 6 metal-metal bonds are there. But how to arrange these metal-metal bonds? How many metal bonds are for a particular metal? So CO is present. We can draw it like, maybe I can put it like this and this. So this will be the actual structure, but we don't know exactly like how to put this. This is the way to put this. We have to know by calculation only. Okay, if you check, there is like 6 metal bonds. Okay, 1 2 3 4 5 6. Okay, so if you see each consider this carbonyl, it is having how many bonds? 1 2 and 3. So each cobalt is having how many bonds? Only 3 bonds. That is why it is having only 3 metal bonds. That is we are going to check. So we know the total number of electrons, right? So the total number of electron is 60 in this case. So I'm going to share this 60 with 4 members. Okay. Then what will be the answer? It will be 15 electrons. Okay. So each cobalt is now having only 15 electrons. It is in short of how many electrons? 3 electrons. So 3 electrons can be given by 3 metal bonds, right? That is why this cobalt is having 3 metal bonds. If you see, this cobalt is having how many metal bonds? This cobalt, 3 metal bonds, because it is in short of 3 electrons. Easily you can find it like this. Okay. Let's move on to the next example. Consider this example: molybdenum and hydrogen, molybdenum and Me2 CO and then cyclopentadienyl CO and then CO. So you have to use neutral method no matter what in the case of bridge. So how to write this in a simplified form means you can write it like MO2, two metal is present, and then these bridged ligands you have to mention mu, and then one hydrogen you can mention, okay, and then bridge ligand, another bridge ligand is present mu and Me2. So basically you can put 2 here, okay. So what this 2 means is mu2 means this particular hydrogen is attached to 2 metal, okay. Consider if it is mu3, then this particular mu3 hydrogen, that means this particular hydrogen is attached to how many metals? 3 metals, okay. So in order to just represent how many metals is present, we are using that mu thing, okay. So that is over. Then how many carbonyl is present? 4 carbonyl, CO4, and then cyclopentadienyl, it will be eta5, and then C5H5 two times. So this is like a simplified form. Even if they give this, you have to bring it to this. That is the only way possible, okay. So what we have to do, we have to calculate the total number of electrons here now, okay. So here for carbonyl neutral means it will be how much? 2. Carbonyl neutral means how much? It is 2. Here also it is 2. For cyclopentaheptacity is 5, so it is 5. So here it 2, 2. So these are very easy. For outer things easily you can put. So now coming to hydrogen. So this hydrogen will have only one electron only. Hydrogen now doesn't have 2 electrons. So 1 electron will only the given contribution. Now this phosphorus, 1 electron is here, 1 electron is here, and totally how many electrons it will have? Almost 5 electrons. So maybe another 1 electron is here, and then 2 electrons will be like a lone pair and it will be a coordinate bond. So basically how many electrons are involved? Here 2 and here 1. Right. This one is just the group itself. Okay. PME2. We cannot consider. So here totally 3 electrons. So P. So Me 2 electron is over. So 1/3 electron and 1 lone pair will be there. So totally 3 electrons are remaining in phosphorus for binding with any one. So 3 is the value here. Okay. So now if you calculate means for molybdenum how many total electrons it is? For molybdenum the total electrons is 6. Okay. So 6 into 2 and then 4 carbonyl compounds. So 4 2s are 8. And then cyclopentadienyl is 2, so 5 2s are 10, and then for hydrogen 1, and then this phosphorus Me2 it is 3. So totally 34 electrons will be there. So this 34 electron is divided between how many? This 2 molybdenum, okay, molybdenum group. So totally 17 electron for each thing. It has to gain 1 electron. Each metal needs 1 electron. So this 1 electron can be given by one metal bond. Okay, so basically there may be a metal bond here. So if you count and see, you can count and check everything is calculating or not. Here 1, this one 1, and then so you can easily count and check whether it is each metal is following 18 electron rule or not. Okay. So this is a very interesting question. So this is carbonyl, mu3 carbonyl, and then Fe4, and then CO12 and 2 minus. Okay. So here first we can calculate the total number of electron, and then later we can find the number of metal bonds and everything. Only one carbonyl is in bridged position, that we can see. Okay. So for Fe the total number of electrons will be 8. Okay. 4s2 3d6, so 8. So 8 into 4, that is 32. 32, and then carbonyl group it is 2, so 12 into 2 is 24, and then for minus 2 we are adding 1 plus 2. So if it is minus 2 we will add plus 2, if it is plus 2 we will minus that 2. Okay, so opposite. Then for this particular group, what will be the contribution? Means for carbonyl we know, consider this is in bridge position, usually it will be like this. Okay, so it already it has used two electrons, and another one and another one. Only 2 electrons is remaining. Okay, so already it has used away its 2 electrons to bind with oxygen. So now 2 electrons are remaining. So one will bind with oxygen, another is binding with the metal, and another metal will give away its electrons basically, because 3 they have given 3, right? So it has to bind with 3 metals. So here what is the contribution of this carbon? Means only this electron and this electron. So this is not considered because that is bonding with the oxygen. So this is the contribution. This two electrons is the contribution. So the contribution here is 2. Okay. So the total number of electrons here will be 60 electrons here. Okay. So now what we have to do? So here actually we need 18 into 4 number of electrons, right? Minus 60. So how many it is in shortage we are going to see. So 72 minus 60 is 12. So now 12 electrons is in shortage for this particular complex. It is either given by the metal bonds, hopefully. Okay. So for that, what we have to do, for one metal bond, it is 2 electrons. So how many metal bonds will be there in 12 electrons? So X is equal to 12 divided by 2. So just cross multiply, you will get it. Okay. So 6 metal bonds. So 6 metal bonds should be there. Okay. So now we have found the total number of metal bonds, but we have to know how many metal bonds will be for each metal. So each metal, how many it will have. So for that, what we have to do, that 60. So this is the total number of electron that I have to share between the 4 metals. How many electrons will be there? 15 electrons will be there. Okay. So how many electrons? This is in shortage of how many electrons? From 18, it is in 3 electron shortage. So these 3 electrons will be given by 3 metal bonds. Okay. So basically each ion is going to have 3 metal bonds. Just remember that. Okay. So if this is the ion, it is 1, 2 and 3 probably. Only 3 metal bonds. So 1, 2 and 3. Okay. Then what about here? 1, 2 and 3. So if you see all the ion is having 3 metal bonds, you can check if it is having total number of metals 6. 1, 2, 3, 4, 5, 6. 6 metal bond is there. Then what we have to check, this carbonyl group. So this carbonyl group should be shared equally between 4. So 12 divided by 4, 4 3s are 12. So each will have 3 carbonyl groups between them. Okay. So each is having 3. Then what about this bridged one? So how to write this bridged one? That is very. So it is bound to 3 metal. They have given 3, right? So what you have to do is consider these 3. 1 and then 2 and then 3. It is bonding to what? A carbon. This is how you have to write the structure. Only 3 metals you have to consider for this bridging position. I hope you understood this. Okay. So what about the contribution? Generally how we can write this in a simple form. So rhodium 2 times that we can write. And then chlorine. Both this chlorine is in like this position. I mean the bridged position. So mu chlorine, that is also 2 times. 2 times this chlorine is present. And then this is what? Hepticity is 3. This is hepticity is 3. Okay, this is also hepticity. Here also hepticity, all of these things, hepticity is 3. This is like the allyl group. Okay, so for that we can write eta 5 C3 H5 2. And then this one also eta 3 C3 H5 2. So both of these things are eta 3 only. Okay, why I have written C3 H5? You can count. Okay, see this allyl group CH2 double bond CH, and then CH2 will be there. See, count the number of carbon 1, 2, 3. If what about the hydrogen? 2, 3, 4, 5. That is why C3H5. Then in the case of cyclopropane, if you see means there will be one bond like this, and then here there will be a positive charge. So this is how it will look. It will not have any negative. This is aromatic. So if you want to know in detail about this, you can watch my previous video on ligand contribution. So basically here one hydrogen will be there, here one hydrogen will be there, and then here one hydrogen will be there. So C3H3, okay, C3H3 will be there, not C3H5, okay. So next, now what we have to do, we have to calculate the number of electrons. For this one, we can easily tell 3, 3, 3, 3. For the main confusion is for the chlorine group, right? For that only we will confuse. So here chlorine have totally 1, 2, 3, 4, 5, 6. Only 6 electron of chlorine. No, 7, right? And then 1, 2, 3, 4, 5, 6, 7. So basically these the rounded lone pairs are there. They are not participating in anything. The rest 3 electrons are participating. So here the coordination bond is there, and here the sigma bond is there, here sigma bond is there, here the coordination bond is there. So basically the chlorine, except this rounded one, all the 3 electrons are participating in something. So the contribution is what? 3. Okay, that is what we have to know. So for rhodium, we can calculate the rhodium, the total number of electrons will be 9. So 9 into 2, and then plus for 3. 3 is there for 4 times, right? This one is also 3, all are 3. So 3 into 4, okay. Then here 1, 3. For 2 chlorine also we can add 3 plus 3, okay. So what will be the total number of electron? It will be 36. If you divide it among 2 metals, it will be 18 electrons each. So there is no need of any metal-metal bonds or anything to attain any stability, okay. I hope you understood this entire concept. Just go through all the examples in Gupta book and also Ajay Kumar said book. So if you have any doubts in any question, you can mention in the comments. I'll be explaining in a particular video about the doubts you have. Okay, thank you for watching my video. Like, share and subscribe my video. Thank you.